When dealing with an earth fault indication in a 110 volt alternating current system, and you cannot isolate any outgoing feeders, there are several methods and instruments available to pinpoint the grounded circuit. Firstly, you should meticulously check all connections and equipment. Inspect all accessible connections, wires, and equipment for any visible signs of damage, loose contacts, or exposed wires that could potentially cause a ground fault. Secondly, consider using a ground fault detector, which is specifically designed to measure the current flowing through the grounding conductor. If a ground fault exists, the detector will register a current spike indicating the presence of the fault. Another useful tool is a clamp-on ammeter. This device allows you to measure the current flow in each individual circuit. In the event of a ground fault, the current in the affected circuit will exhibit a higher than normal reading compared to other circuits. Beyond these general techniques, there are specialized instruments engineered for detecting ground fault current in a live circuit. One such instrument is the ground fault current interrupter, or GFCI. A GFCI functions by detecting any difference between the current flowing in the supply wire and the current returning in the return wire. If a ground fault is present, even a small difference will cause the GFCI to trip, immediately interrupting the circuit and preventing potential hazards. Another similar device is the residual current circuit breaker, or RCCB. Like the GFCI, the RCCB monitors the current balance between the supply and return wires. However, the RCCB possesses the added capability of tripping in response to a ground fault in a downstream circuit, providing broader protection. The earth leakage relay, or ELR, is yet another instrument designed for ground fault detection. An ELR continuously monitors the current flow through the grounding conductor. If the current exceeds a predetermined threshold value, the ELR will trip, effectively interrupting the circuit and mitigating the risk associated with the ground fault. For all electrical work, especially when dealing with live circuits, strict adherence to safety precautions is absolutely essential. Prior to commencing any troubleshooting or testing, verify that you possess the necessary training and equipment to minimize any potential risks. Always wear appropriate personal protective equipment such as insulated gloves and safety glasses. Utilize insulated tools specifically designed for electrical work. Before testing, visually inspect the area for any potential hazards, such as wet conditions or damaged equipment. Always work in a well-lit environment to ensure clear visibility. If you are unfamiliar or uncomfortable with any aspect of the testing procedure, seek guidance from a qualified electrician. Proper grounding is a cornerstone of electrical safety. Grounding provides a low resistance path for fault current to flow back to the source, causing the overcurrent protection device, such as the circuit breaker or fuse, to trip and to energize the circuit. This prevents dangerous voltage from being present on equipment enclosures and other conductive surfaces, reducing the risk of electric shock. Electrical codes, such as the National Electrical Code, or NEC, provide detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure that electrical systems are installed and maintained in a safe manner. Understanding and adhering to these codes is crucial for preventing electrical hazards. Effective troubleshooting of ground faults requires a systematic approach. Firstly, gather information about the system, including its voltage, current, and grounding configuration. Review any available electrical diagrams or schematics to understand the circuit layout. Secondly, visually inspect the system for any obvious signs of damage or loose connections. Look for burn wires, cracked insulation, or corroded terminals. Thirdly, use appropriate test equipment to measure voltage, current, and resistance at various points in the circuit. Compare these measurements to expected values to identify any anomalies. Fourthly, isolate the fault by systematically disconnecting sections of the circuit until the fault disappears. This can help narrow down the location of the ground fault. Finally, once the fault is located, repair or replace the damaged components. Ensure that all connections are properly tightened and that the system is retested to verify that the fault has been resolved. Ground fault protection devices, such as GFCIs and RCCBs, play a vital role in preventing electrical shocks. These devices are designed to detect even small ground faults and quickly interrupt the circuit, preventing dangerous current from flowing through a person's body. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. RCCBs are typically used in residential and commercial electrical panels to provide protection for entire circuits. Regular testing of ground fault protection devices is essential to ensure that they are functioning properly. GFCIs should be tested monthly by pressing the test button and verifying that the device trips. RCCBs should be tested periodically by a qualified electrician. Proper maintenance of electrical systems is crucial for preventing ground faults. This includes regularly inspecting and tightening connections, replacing worn or damaged wiring, and keeping electrical equipment clean and dry. Over time, connections can loosen due to vibration or thermal cycling, leading to increased resistance and potential overheating. Damaged wiring can expose conductive surfaces, creating a path for ground faults to occur. Dirt and moisture can also contribute to corrosion and insulation breakdown. By addressing these issues proactively, you can reduce the risk of ground faults and maintain a safe electrical system. Understanding the principles of electrical safety and the proper use of test equipment is essential for anyone working with electrical systems. Always follow established safety procedures and seek guidance from a qualified electrician when needed. Electrical work can be dangerous, and it is important to take precautions to protect yourself and others from harm. The NEC is a comprehensive set of standards for electrical installations. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is updated every 3 years to reflect changes in technology and best practices. Compliance with the NEC is mandatory in many jurisdictions. Understanding and applying the NEC requirements is essential for ensuring the safety and reliability of electrical systems. Grounding and bonding are two distinct but related concepts in electrical safety. Grounding refers to connecting an electrical system or equipment to the earth, providing a low resistance path for fault current to flow. Bonding refers to connecting together all metal parts of an electrical system or equipment, creating an electrically conductive path that can safely carry fault current. Both grounding and bonding are essential for preventing electric shock and fire hazards. The NEC provides detailed requirements for grounding and bonding electrical systems. These requirements vary depending on the type of system and equipment. Proper grounding and bonding is crucial for ensuring the safety and reliability of electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the rated capacity of the wiring or equipment. Short circuits occur when there is a direct connection between two conductors, bypassing the normal load. Overcurrent protection devices interrupt the flow of current when an overload or short circuit occurs, preventing damage to the wiring and equipment and reducing the risk of fire. Circuit breakers are resettable devices that can be tripped manually or automatically. Fuses are one-time devices that must be replaced after they blow. The NEC provides requirements for selecting and installing overcurrent protection devices. These requirements are based on the type of circuit, the size of the wiring, and the load being served. Proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. Electrical panels, also known as load centers or breaker boxes, are the central distribution point for electrical power in a building. They contain circuit breakers or fuses that protect individual circuits. Electrical panels must be properly sized to accommodate the total load of the circuits they serve. They must also be properly grounded and bonded to ensure electrical safety. The NEC provides requirements for installing and maintaining electrical panels. These requirements cover topics such as panel location, wiring methods, and overcurrent protection. Proper installation and maintenance of electrical panels is essential for ensuring the safety and reliability of electrical systems. Wiring methods refer to the techniques and materials used to install electrical wiring. Common wiring methods include conduit cable and raceway. Conduit is a rigid or flexible metal or plastic tubing used to protect and enclose electrical wiring. Cable is a factory assembly of two or more insulated conductors. Raceway is a channel designed to hold and protect electrical wiring. The NEC provides requirements for selecting and installing wiring methods. These requirements are based on the type of application, the environment, and the voltage and current of the circuit. Proper wiring methods are essential for ensuring the safety and reliability of electrical systems. Electrical equipment must be properly installed and maintained to ensure safe and reliable operation. This includes following manufacturer's instructions, using appropriate wiring methods, and providing adequate ventilation. Electrical equipment should also be inspected regularly for signs of damage or wear. Damaged or worn equipment should be repaired or replaced promptly. The NEC provides requirements for installing and maintaining electrical equipment. These requirements cover a wide range of equipment, including motors, transformers, and lighting fixtures. Proper installation and maintenance of electrical equipment is essential for ensuring the safety and reliability of electrical systems. Arc flash is a dangerous electrical hazard that can occur when there is a fault in an electrical system. An arc flash is a sudden release of electrical energy that can cause severe burns, blindness, and even death. Arc flash hazards can be mitigated by using appropriate safety procedures and personal protective equipment, or PP. Safety procedures include de-energizing equipment before working on it, using insulated tools, and maintaining a safe distance from energized equipment. PPE includes arc-rated clothing, gloves, and face shields. Arc flash studies can be performed to determine the potential arc flash hazard at a particular location. The results of these studies can be used to select appropriate safety procedures and PPE. Electrical safety training is essential for anyone working with electrical systems. Training should cover topics such as electrical hazards, safety procedures, and the proper use of test equipment. Training should also be specific to the type of work being performed and the equipment being used. Regular refresher training is also important to ensure that workers stay up to date on the latest safety procedures. Lockout/tagout is a safety procedure used to prevent accidental energization of equipment during maintenance or repair. Lockout involves placing a lock on the energy isolating device, such as the circuit breaker or disconnect switch, to prevent it from being turned on. Tagout involves placing a tag on the energy isolating device to warn others not to turn it on. Lockout/tagout procedures must be followed whenever equipment is being worked on to prevent accidental energization. Electrical safety audits can be performed to identify potential electrical hazards and ensure compliance with safety regulations. Audits should be conducted by qualified personnel with experience in electrical safety. The results of the audit should be used to develop a corrective action plan to address any identified hazards. Regular electrical safety audits can help to prevent accidents and injuries. In addition to the specific methods and instruments discussed, it's beneficial to cultivate a general awareness of potential hazards and safe work practices when dealing with electrical systems. This includes recognizing warning signs of potential problems such as flickering lights, unusual noises, or the smell of burning insulation. It also includes practicing good housekeeping in electrical areas, such as keeping them clean and free of obstructions, regularly inspecting electrical cords and plugs for damage, and avoiding overloading circuits by plugging too many devices into a single outlet. These simple precautions can significantly reduce the risk of electrical accidents. When troubleshooting ground faults, it's sometimes necessary to use a process of elimination to isolate the problem. This involves systematically disconnecting portions of the circuit until the ground fault disappears. While this can be a time-consuming process, it's often the most effective way to pinpoint the exact location of the fault. It's important to note that this process should only be performed by qualified personnel who are familiar with electrical safety procedures. Another useful technique for troubleshooting ground faults is to use the circuit tracer. A circuit tracer consists of a transmitter and a receiver. The transmitter is connected to the circuit, and the receiver is used to trace the path of the current. This can help to identify the location of a break in the circuit or a ground fault. Circuit tracers are particularly useful for troubleshooting circuits that are hidden behind walls or in conduits. When working with electrical systems, it's crucial to use the right tools for the job. This includes insulated screwdrivers, pliers, and wire strippers. It also includes a reliable multimeter for measuring voltage, current, and resistance. Using the wrong tools can damage the equipment and increase the risk of electrical shock. Always inspect tools before each use to ensure that they are in good working condition. Regular maintenance of electrical equipment is essential for preventing ground faults and other electrical problems. This includes cleaning electrical panels, tightening connections, and replacing worn or damaged components. Maintenance should be performed on a regular schedule according to the manufacturer's recommendations. Keeping electrical equipment clean and well maintained can significantly extend its lifespan and reduce the risk of failure. When working with electrical systems, it's always best to err on the side of caution. If you're not sure about something, don't hesitate to ask for help from a qualified electrician. The electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from harm. Remember to always prioritize safety and follow established procedures when working with electrical systems. This comprehensive approach to finding and addressing ground faults in 110 volts alternating current systems, incorporating safety precautions, the use of specialized instruments, and a systematic troubleshooting methodology will enhance electrical safety practices.